Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we are going to learn about recursion. Recursion is something we've all likely heard of, so let's start with a definition. A recursive function is a function that calls itself. Recursion is a method of solving a problem where the solution depends on solutions to smaller instances of the same problem. So after hearing this definition, you're probably thinking to yourself, I still don't get it. And that's okay. Recursion can be very intimidating and a complex topic. When you try to learn it, you're typically bombarded by buzzwords and math symbols. So in this lesson, I really want to start from the beginning, take the basics, and then build on top of things you already know and understand. And by doing this, I really think we can get a strong foundation in recursion and then be prepared to start answering these coding interview questions so then we can understand it even more deeply. So when we're solving problems in interviews, we often just take an operation, repeat it many times, build up this solution, and then eventually we calculate the answer. This is what we call our algorithms. It's that logic that builds the solution. And to build the solution using this logic, there are two common strategies: an iterative solution and a recursive solution. The iterative approach is probably the one you're most familiar with, and what it does is use simple loops and build up this problem from the beginning. So for example, for a factorial, if we did it iteratively, we would start with 1, because that's the smallest factorial, and then we would continue to multiply numbers together until we found the solution we wanted. So for 4 factorial, we would start with 1, and do 1 times 1 is 1, and then we would do 1 times 2 is 2, 3 times 2 is 6, 6 times 4 is 24, and that's how we calculate the solution iteratively. And recursion and iteration are the same thing, just a different approach. So anything that can be done iteratively can also be done recursively. So what we do with a recursive function is we start at the other side. We represent the solution we want, and then begin calling it with smaller and smaller values each time until we reach a base case. So we get to that smallest value, which is the point where we started the iterative solution. So with 4 factorial, we know we can represent 4 factorial as 4 times 3 factorial, and then 3 factorial is just 3 times 2 factorial. 2 factorial is just 2 times 1 factorial, and 1 factorial is just 1. And 1 is our base case. And these are really the two key components of recursion. You have this base case, or the stopping condition, where you finish your recursive calls. And then you have the recursive case, where you're building up this logic. So the base case is what allows the function to end. So we stop calling it recursively and return a constant value. By returning a constant value, it solves two things. It prevents the recursion from continuing. So instead of going down here to continue to call it recursively, we just return a constant. But then the function that called this, the one that passed in 1, now returns a constant value here. So its recursion is done as well because it has two numbers that it can multiply together. So finding the base case is what allows us to return a constant value, and this constant value is what allows us to unwind our recursion, so we can actually begin calculating these solutions. So just like the iterative case started with 1 and multiplied them together, with recursion we start with the number we want, we calculate it down to this same value, and then build them up. So we start multiplying them together to calculate the solutions. So let's walk through what's happening with this recursive solution. We want to calculate 4 factorial. So we just call the factorial function with the number 4. So we're expressing the value we want, 4 factorial, in exactly the same way. So with recursion, we're expressing the solution that we want. We don't start by building it up from the beginning. We start at the top, indicating the final answer that we want to calculate. And we know the factorial of 4 is just 4 times 3 factorial. So this is where that recursive logic is coming in. We are solving it with smaller values each time. So we say 4 times 3 factorial, the logic or our recursive case. But now we need to calculate 3 factorial, so we also pass it into the function. Well, 3 factorial is just 3 times 2 factorial. So the recursive case, we say 3 times factorial of 2. And once again, we're just calling it with smaller values, so we need to calculate that. Then 2 factorial is just 2 times 1 factorial, so we're calling it with the smaller value again. And finally, we reach our base case. We know 1 factorial is just 1. So we continue to solve the same problem multiple times by calling it with smaller values each time until we reach the base case, which is the smallest value. This is the end of the recursion and will return a constant. So now we can return this value and now calculate the solution to the function that called that. So instead of 2 times the factorial of 1, we now replace it with just the value of 1. So we can calculate the solution to this problem because the function that it called returned a value. Then we return 2 up the chain again. We replace factorial of 2 with 2. So now we have 3 times 2, or 3 times 2 times 1, which is 6. Then we return this value up to the function that called it. And we have 4 times 6. But if we looked at the logic that got us here, it was 4 times 3 times 2 times 1, which is exactly the factorial. So 4 times factorial of 3, recursively call these functions. Then they started returning their solutions up to our original call, which gives us the solution of 24. So there are 2 key components of a recursive function. That recursive case, where you write out the logic that will solve the problem, and you can express it by calling the recursive function multiple times with continually smaller input each time. And you do this until you reach the base case. The base case allows you to stop the recursion and also returns a constant value that can then be used to calculate the solution to the function that called it, and then build up these solutions starting from the base case back to the original function invocation. There is one key concept to remember with recursion, and that's stack overflow. Our computers have a limited amount of memory, and when you call a function, it gets added to the memory, or the call stack. And if you call too many functions recursively, they continue to build up. And if either it calls too many times or you forget your base case, then your computer is going to run out of memory. And this is what we refer to as a stack overflow, and your program is going to crash and not be able to calculate the solution. So this is one of the big downsides to recursion. It adds memory to the call stack, so this counts against your big O space, and if you run out of memory, it can crash your program. So this is often why we prefer iterative solutions over recursive functions, but sometimes recursion is just much more elegant and the best way to approach a problem. However, it's worth noting that if your language has tail call optimization, it actually doesn't incur space on the stack, and this is something that you need to check with your language, and you'll likely need to note it to the person interviewing you. And now let's code out our factorial function recursively to understand what's happening. So when we call factorial of the n, we're calculating the nth factorial number. I'm going to add a debugger so we can step through it. We have our base case, which is if n is less than or equal to 1, we just return 1. This is a constant value that we don't have to calculate. We know that we can calculate the factorial of any number n by multiplying n times the factorial of all the numbers before it. So for example, if we wanted to calculate 5 factorial, we know it's 5 times 4 factorial, and we know 4 factorial is just 4 times 3 times 2 times 1. And we know that 5 factorial is just all these numbers multiplied together. And we could also see that 5 times 4 times 3 factorial is going to be equivalent to this as well. So it's this logic that if we keep solving it with smaller and smaller input, we'll eventually reach the base case and can get our solution. And finally, we return the answer. So the recursion is happening here, where we just call the function inside of itself. And we pass it a smaller input. So to calculate factorial of the n, we need the factorial of the n minus 1. So using that smaller input is how we eventually reach the base case. We can calculate the solution to all the smaller problems to eventually combine them to get the overall solution. So let's find the factorial of 5. So when we step through, we see that n is initially 5. So we skip the base case. Then we do 5 times the factorial of n minus 1. Well, now we call this recursively. So we go back to the top of the function because we're calling it again. So now this one is added to our call stack. But this time n is 4. We skip the base case again. Well, now we can't continue on until we calculate the factorial of n minus 1 again, which is 3. So now this function is added to our call stack. And we keep doing this, eventually until we reach 1. So now we enter this if statement and return 1. And now we're back in the previous function, where n was 2. So n is 2. Factorial of n minus 1 is 1. So now we have the answer for this step as 2. We return that, and now we're back to the function where n was 3. So n is 3. Factorial of n minus 1 is 2. Then the answer is 6. And then we return that up again. N is 4. And we have 4 times the factorial of n minus 1, which is 6. And then when we multiply those together, it's 24. And we return 24 to our original function invocation, where we wanted to calculate the factorial of 5, where n is 5. So we have 5 times 24, which is 120. That's how you calculate the factorial of 5 recursively. One of the biggest drawbacks to recursion is that it uses memory to track the function calls, which counts against our big O space. But also, if the input is too large to the recursive function, it can use all the available memory, which will cause a stack overflow and crash the program. To simulate this and visualize a stack overflow, let's remove the base case so that the recursion will continue to add functions to the call stack without being told to stop, which will cause an overflow. So if we call factorial of 5 again, well, now we have maximum call stack size exceeded. There were too many functions added to the call stack, so our program ended without being able to calculate the solution. And we can see that here, where we just continued to call the factorial function without ever ending. And those are the key concepts of recursion. Let's dive into some questions and figure out how to use it.